What's up, y'all? It's Afueko. It's finally the last episode. Honestly, I'm excited to move on from these libraries. Today, we're going to be training a DCGAN to generate faces. We saw this in episode 5 of this series, where we generated fake fashion images using the Fashion MNIST dataset and the DCGAN model. We're going to be using that model to generate faces that somewhat look like the members of Destiny's Child, using the dataset that we generated in the last episode. After we go over model design and training, we'll notice that the results are okay, but nowhere near other generative methods that exist today. So go over the model architecture of two more powerful methods, the progressive GAN and the style GAN. If you want the code for this video, it'll be at this link, which is also in the description. Let's get into it. The way the PyTorch API works is quite similar to Keras in the TensorFlow library with eager execution. Dataset loading is done using the Torch Vision datasets image folder class, which loads datasets stored in image folders just like we did with the TensorFlow Keras data loader. Our model design is the simplest generative adversarial network we can create. A generative adversarial network is a type of network that learns to generate fake instances of a type of image. In this example, we'll create fake faces. The reason why this network is called adversarial is because it learns two opposing tasks simultaneously. The system itself contains two separate networks that are optimized jointly. The first network is our generator, which creates an image given a feature vector. The feature vector is typically initialized as random noise with a simple DCGAN. The second network is the discriminator, and this network learns to determine whether or not an image is real or fake. During training, we train our generator to create fake images that fool our discriminator while simultaneously teaching our discriminator to identify a fake image. As both networks reach convergence, we get better at creating fake images, but also we get better at determining whether or not these images are fake. The training algorithm is pretty straightforward once you understand the model design. We first take the real image and calculate an error based on the discriminator identifying that image as real. Then we generate a fake image and calculate a second error term based on properly identifying that generated image as fake. If this is all that we did, our model could just easily converge to generating noise and identifying real images properly. So in our last step of training, we create a third error term based on classifying that fake item as real. This is why we consider the system adversarial. We just calculated an error based on this generation being fake, and now we're calculating an opposing error based on this generation being real. This is why for that last loss element that we print, we have two different values during training. Looking at the results over time, we see that at each epoch, the structure of our images gets closer and closer to something that resembles a face. However, the faces do have this weird warped quality to them, and this is even worse for the Michelle only generator, which has the least amount of training data. Increasing the size of the dataset will definitely allow us to create better fakes, as seen in this PyTorch tutorial that generates fake faces trained on the Celeb A faces dataset. Rather than just increasing the size of our dataset to create better results, a few variants of this type of model architecture exist that allow us to create much higher resolution and higher quality fakes. The first is the Progressive Generative Adversarial Network, or PGAN. PGAN learns to create fakes at increasing scale sizes. We start by generating fakes at the smallest scale in our range, and over time we add more layers to increase the resolution of our fakes. With the PGAN, we learn a decently stable representation at each scale, and consequently, the training of larger models start off with a better set of weights. Now we're not going to train this in this video because these models require you to train each scale independently. It can end up taking days or weeks to train, let alone debug on new datasets. However, the PyTorch GAN model zoo on GitHub has predefined models and training procedures if you want to use it for your work. The second variant is a style-based GAN. Now, this is a bit more complicated, but extremely powerful, so be careful to read the paper before you use it. But anyway, this model gives us much more control over the output of our fakes. The details are a bit dense, but if I were to simplify it, the network successfully learns spatially invariant styles from our source images, and one can actually pass in some rough structure that allows us to have some idea of what the fakes are going to look like. This allows us to do things like change the hair color or scenery of fake facial images to match others, as seen in the paper. There are also really cool things you can do like style mixing, but definitely read the details if you're more interested. That's it for this video, and we're also done with this series. If you made it this far, comment down below what kinds of things would you want to see on this channel. And if you enjoy any of the videos on my channel, definitely like, comment, and subscribe to my channel, and also hit that notification bell so you're notified whenever I post a new video. That's it for this video, and I'll see you on the next one. Later. I don't need the fame, and I don't like the games, and I don't like the way you want me to be wife now. I'm in it for the game.